This lecture introduces matrix arithmetic, such as matrix addition, matrix subtractions, and matrix multiplications. But first, we need to introduce matrix notations. So if A is an m by n matrix, then A has m rows and n columns. Okay, and then you can represent matrix A with its entries. So you have m rows and n columns. That means in matrix A's, you would have n times n number of entries. And each entry is represented using indices, right? Each entry would have 2 digits of indices. The first digit represents the row order. So if you have little a 1 1, that means this entry here is in the first row and the first column. All right. And then if you pick another entry, let's say, for example, if you look at the entry A34, that means this entry here is the entry in the third row and fourth column. Okay, so you can use entries to represent a matrix, or a matrix can be written in this form. Big A, matrix A equals to parenthesis little a, indices ij, where I is a number of rows. So I is from 1 to m. And then j is the number of columns. So it should be from 1 to n. All right. Okay. And m by n is the dimensions or the size of matrix A. So m by n would tell you the number of rows and number of columns. That's why it can be called as the dimension or the size of matrix A. So now in matrix A, we can represent a matrix using its vectors. You can use either a row vectors, or column vectors of a matrix to represent a matrix. So a row vector is in the form little ai with an arrow above a represents a row vector, right? And a column vector, let's say b sub j equals to a vector that has n, because this is a column vector, so it should have n, it should have m entries in these vectors here. So in a matrix A, you can use either column vector to represent a matrix. So when you write A equals to A1, A2 to AN, that means A1 here is the first column vectors of A. A2 here is the second column vectors of A, and so on and so forth. And then if you represent a matrix A using its row vectors, you have to use, because it have m rows, so you have m of the row vectors, and each of the vectors will have an arrow above the vector letter. Okay. So again, if you use vectors, that means if you use column vector to represent A, so you can see that you have A1, A2, AN. You have n vectors, columns, right? And if you use row vectors to represent A. So you have A1 with an arrow, right? A2 with an arrow. So this is first row vector, the second row vectors, and you have m rows, so you should have m of the row vector. And each of the row vector will be vectors in this form. Okay, then you will have, because you have n columns, so then you will have n real numbers in this row vector. Because if you look at the column vectors, because you have m rows, so you're expecting to have m real numbers in a column vector. Okay, so since we will be working with column vectors exclusively, we'll refer a column vector in Rn as a vector, and the standard notation for a column vector is a letter, let's say x, and is a bold-faced lowercase letter. Okay. So for an example, if x is a column vector, then we use bold-faced lowercase x to represent x as a column vector. Later on, if you want to use A as a column vector in a matrix A, for example, and then if A1 is the first column vectors in matrix A, then you can use letter A sub 1 in a bold face lowercase a1, and then if you have m number of columns, then you will have na1 and a121 down to am1. All right, so it's just the first column vector of the matrix A, and if you have n columns, then you should have n number of column vectors in matrix A. All right, so once we know notations for matrices, and if this is the definitions of inequity, equal or equal matrices. So the two matrices A, little aij, and B, little bij, if they both have the same size or dimensions, right, let's say m by n, then they are said to be equal if each of I and j, for each of I and j, little aij equals to little bij, for each of I and j. For example, so let's say I equals to 2 and j equals to 5, then a25 should be equals to b25, right? You pick any I and j, aij equals to bij. If that satisfies, then the two matrices A and B are said to be equal. So now we can talk about matrix arithmetic. First, scalar multiplications. So if you have a matrix A, size n by n, you multiply a real zero, a real value to A, you scale the matrix A by alpha. That means you multiply alpha to matrix A. And if you multiply a constant or a real value to a matrix, make sure that you multiply that constant to every single entry of the matrix. Every single entries of a matrix. Okay. And then if you add the two same size matrices together or subtract them, then you would take A11 plus B11 will be the result of the first entry on the first column and first row of the sum or the difference matrix. And then you need to, in other words, you just need to add or subtract. If you have a subtraction, then you have to subtraction here. You add or subtract all corresponding entries of the two matrices, right? When you add or subtract the two entries from A and B, and those two entries have to come from the same row and the same column. And the next arithmetic is, next operations of matrices is matrix multiplications. So before we can try to multiply the two matrices, we need to make sure that the size or the dimension of two matrices work. How does it work? If you have a matrix A and a matrix B, Let's say m by r is the size of matrix A and r by n is the size of matrix B. When the number of columns in matrix A is the same as the number of rows in matrix B, then you can multiply these two matrices together in the order A times B. All right. Before you can multiply the two matrices together, you need to make sure that the inner, is inner dimensions, right, of these two matrices here are a match. And the outer dimension m and n here aren't matter. So if you have these two matrices with this size is m by n, m by r, multiplied to r by n, then the product C will be of the size m by n. So you see that the outer dimensions of A and the outer dimensions of B will produce the dimensions of the product of the two matrices here. Okay, so R and R has to be the same, and the products of the two matrices has this dimensions of m by n. Okay, and how can you come up with each of the entry in the product C? So each of the entry in the product C, so say C, little c I j, okay, equals to the dot products of the row AI with the column BJ. Okay, so this is the row vector and this is the column vectors. So you get the row AI from matrix A and you dot product with the column J from matrix B. What is the dot products? So the dot products is actually the sum of all the products of the two corresponding entries from the two vectors. So let's say if you have, so let's talk about the dot product so real quick, right? So let's say if, for example, so I want to talk about the dot products. For example, if I have a vector A as a row vector, 1, 2, okay. And I have a column vector, let's see, 3, 4. Okay. Then if I want to take the row vector A and I want to dot product with the column vector B here, I will take the products of the first entry of row vector A, 1, and I multiply to the first entry of the column vector B. So it's going to be 1 times 3. This is the product. And I add to the product of the second entry of row A to the second entry of column B, which is 2 times 4. So the result of this product is 3 plus 8, which is 11. Okay. So you take the products of the corresponding entries of the two vectors and you add them all together. That is the dot products. And for each of the entry in C, again, C is the products of the two matrices A times B. You're going to use the dot products of a Cij equals to the dot products of the row AI multiplied to the column Bj. All right, let's do some example. So let's look at if we have the actually these 4 matrices. So the first matrix A has the dimensions of 3 by 3, right? So you have 3 rows and 3 columns. The second matrix B has the dimensions of 1 by 3. And if you look at this matrix B here, you can say that matrix B has 1 row vector. Okay. has only one row vector and has 3 column vectors and 1 row vectors. All right, so matrix C has the dimensions of 3 by 2. Again, 3 rows and 2 columns. Matrix D has the dimensions of 3 by 3, is 3 rows and 3 columns. All right, so now let's try to see if we can find this first arithmetic, this first expressions, 2 times A plus 3 times C. Well, I can find 2A. I can multiply 2 to all the entries in A of A, right? And I can find 3C. I can multiply 3 to all the entries of C, but can I add the 2A plus 3C together? The answer is I cannot, because they are not sharing the same size or the same dimensions. If the two matrices are not sharing the same size or the same dimensions, you cannot add or subtract them. Okay. Sometimes, in some case, you can actually multiply them, but you cannot add or subtract them. So we cannot do the first operation, or the first expressions is not doable. How about A times B? So A has the dimensions of 3 by 3, and B has the dimensions of 1 by 3. And you can look at the inner dimensions here, they're not the same. If they're not the same, then this matrix multiplication cannot be done. How about C times D? So again, C times D, we look at the dimensions of C and D, and we look at the inner one. They're not the same. We cannot find the product of C and D. Okay. How about D times C? So C times D is not doable. How about D times C? D times C, so if you have matrix D as dimension of 3 times 3, and the matrix C, right, has the dimensions of 3 times 2. This is dimensions from C. And we look at these two matrices here in the reverse order. So then you can see that the inner dimensions here are the same. That means we can go ahead and do this matrix multiplications. Okay, and the result of this matrix multiplications should be should has the dimensions of 3 and 2, 3 by 2. Okay, so the matrix the products D times C is doable, and the dimensions of this product is 3 by 2. Let's go ahead and try this matrix multiplications. So D, I want to rewrite matrix D 1, 3, 8, and -3, 7, 2, and then 0, 2, 3. And then I have the matrix C, right? This is D and this is C. So matrix C is 7, -0, 0, -1, 3, and 5. All right. So this is C and this is D. Okay. And then the products will have 3 rows and 2 columns. So I say 1 rows, 3 rows, 2 rows, and 3 rows, right? And you have only 2 columns. So the total number of entries should be 6, right? And I call this, each of this here is DC 1, 1, right? DC 1, 2, DC 2, 1, DC 2, 2, DC 3, 1, DC 3, 2. Okay, so I have 6 entries for this product, and how I can find the entry, the first entry, DC11. So DC11, you would, in order to find DC11, you want to dot products like D, the row vectors D1 with the column vector C1. Okay, and the row vector D1 is the first row of D and the first column of C. So I just dot product these two vectors together to get DC11. And the dot products is gonna be, so take 1 multiplied to 7. Okay, add 3 multiplied to 0. Add 8 multiplied to 3. And which equals to 24, 7, 31. Okay, so 31 will be my first entry, DC11. How about and from here you get to this one. All right, if you want to get DC12, it will be, you take the row the row vector D1 and you dot product to the second column C2. So D1 is here, this is D1, and then now I need to take C2. Okay, so the dot product will be 1 times -2 plus 3 times -1 plus 8 times 5. Okay, which is 40, -3, -35. 35 will be the entry DC12. And you can see that this is how we're gonna fill out all of these entries of the products here, right? Let's go to the next one, DC21. So DC21, you can use D2, the second row of D, and dot product to C1. So the second row of D is here, and C1 is still here. So you can multiply it. Okay. So it's gonna get -3 times 7 plus 7 times 0 plus 2 times 3, which is 6. -21 plus 6 is -15. Okay, -15. All right, so next, I want to find DC22. DC22. So you get D2, right? The row vectors of D2 multiplied to the second column of C. So again, the 2, row 2, column 2. And you just need to dot product it. So you take -3 times -2 plus 7 times -1 plus 2 times 5. Okay, which you get -6. 6, -7 is -1 plus 9, but 10 is 9. So the answer should be 9 here. Okay, let's 2 more. Let's keep doing it. You get, you want to find DC31. Okay, that means you take the third row of D and you dot to the first column of C. So the third row of D and the first column of C. Okay, the first row of D will have 0 times 7 plus 2 times 0 plus 3 times 3, which is 9. All right, last entry, DC32. So the third row of D and the second column of C. So you have this. So you will take 0 times -2 plus 2 times -1 plus 3 times 5, which is 15 minus 2 is 13. So now we just finished a matrix multiplications problem, and the result is 31, 35, -15, 9, 9, and 13. Okay. Again, I just show you how to do a matrix multiplications of the two matrices. And remember, before you can go, we're trying to do all this dot products of all those rows, vectors, and column vectors. You need to make sure that the dimension works before you proceed this process. Again, the dimensions for matrix multiplications is the inner dimensions here has to be the same. If they're not the same, then you cannot multiply them together.